Theta, a lot of times when we're using theta, we actually mean theta to be a variable. How about pi? When you see pi, you don't just see a letter or a variable, you understand pi to be what? 3.14. Like, pi is 3.14. So remember in geometry, you used to do like area of a circle, circumference of a circle, and then you also did like volume and surface area for cylinders and cones. And a lot of times your geometry teacher would say, I want two answers. I want one answer in terms of pi, and I want one answer that's a decimal. So you would do like the volume of the cone is 100 pi centimeters cubed, and then you'd have to write a second answer that said like 314.2 centimeters cubed. Okay, so we understand that there are some numbers, or some letters already that are numbers assigned to a particular number. The same goes for the letter E. We are going to say E is no longer a letter. E is now a number. And don't write this down just yet. I got a typo there. There, it's fixed. E is the number 2.71828. Blah, blah, blah. You will need a calculator today, so I would recommend getting out your calculator. It should be like a scientific calculator so that you have the E function on it. If you're using your cell phone and you're going to be using your cell phone at home for homework, I'm totally okay with that. But I would still encourage you to come up and grab one of mine for the class period, because on a quiz or a test, you're not going to be allowed to use your cell phone, but you're going to need to know where to find the E button. The number E is irrational, meaning its decimal representation does not terminate or follow a repeating pattern. The other letter that you know is a number, pi, is also irrational. Pi is irrational, never repeats, never ends. We know that. We know we can go to YouTube and Google people who have memorized thousands of digits of pi. That would be a really interesting video to watch. Okay. The number that is a letter that Jackson gave us, I, would not necessarily be considered irrational because it's not even a real number, right? Irrational is a category for real numbers. So we would just say like I is a special number that we use as a letter because it's imaginary. So every time we assign a number a letter name, it's because there's something interesting happening. We can't just like call it a number like 10, okay? So we give it a letter instead. Now, I want to show you where your E button is on your calculators. So most of you in your calculators will have to follow this method. You'll have to use your second button, which on like Casio's is shifting. And then you probably have a button somewhere that is labeled LN. And above the LN in your like shifting color, you should be able to see like an E to the X. So go ahead and pull that up. If you have a calculator like mine, most of you, when you type this, will get an E with a caret, which that's raised to, and then a parentheses, which that's awesome if your calculator brings that up. Does anybody have the little calculator that goes backwards? Eric has the calculator that goes backwards. Anybody else got that backwards calculator? Okay. Eric, you will have to, we're going to type E and then our exponent. You'll have to type your exponent and then second ln. Okay, so we're going to do E to the first. So everybody type a 1 after your parentheses. Eric, you type 1 second ln. What does your calculator say on the screen then? isn't that interesting? Your calculator is giving you the number that I told you E was, right? So E to the first is 2.71828, other stuff, right? Okay. Let's just make sure everybody's calculator is working and Eric gets to practice again. Let's do E squared. Can you calculate E squared for me? Let me know if you can't find your E button. I'll come over and help you if you're having any issues. Okay, I'm going to stop at 7.389. And then we'll know if we're on the right track. Anybody not able to get 7.389? Okay, so make any notes in your notebook about how to use your calculator. I'll assume that, like, for your very first quiz, which will happen next week, that you know where the E button is on the calculator and that you can use it. Okay. Now, some people may ask, why is E 2.71828 not repeating? Okay. Well, here's a little story. So, you are, on average, I know I have some younger and some older, I'm going to say 16 years old. Okay. So, let's say today's your birthday, and you're turning 16. Does your body stop and wait for 365 days until the eve of your 17th birthday, and you go to bed and your birthday happens, and then you wake up and you've grown 3 inches and all these things have changed? You're saying, no, that is not the way that works, Ms. Cronky. How do you grow? Gradual. All the time. Right now, as you're sitting in front of me, you have cells in your body that are dividing, okay, going through the process, allowing us to grow, things like that, okay? So, why is E called a natural base? Because that's what happens in nature. In nature, we, creatures of nature, we grow all the time. We don't grow on a schedule. So this comes from the compound interest formula. Do you remember this formula? A equals P times 1 plus R over N raised to the N times T. And the banks use this to say, instead of me giving you interest one time a year, I'm going to give you a little bit of your interest throughout the year so that you can earn interest on some of your interest. Okay? But this would be like us saying, instead of just growing one time in the year on our birthday, we actually grow all throughout the year very gradually, bit by bit, all the time. And then it would be like, well, do we grow quarterly? Do we grow monthly? Do we grow daily? Do we grow every minute? Do we grow every second? We just grow all the time, don't we? We don't run on a schedule. So nature doesn't run on that schedule. One way we can see how E gets calculated is, we're going to let P equal 1, we're going to let R equal 1, and we're going to let T equal 1. So we're going to make a really boring equation here. It's going to look like 1 for P times 1 plus 1 over N raised to the N times 1. Because I made all P, R, and T were 1. And then I really don't need this N times 1 is really just N. Put my eraser down. Oh man, that's just a disaster. N times 1 is really just 1 in the numerator, and I don't need the 1 in front, so it's really just 1 plus 1 over N raised to the N, if I simplify that. Okay. And then I could go through this issue. Do I compound annually? Do I compound quarterly? Do I compound monthly? Do I compound daily? I could put numbers in for those. Do I have anybody who's a fan of Broadway musicals and knows the song from Rent? How many minutes are in a year? No musical fans? 525,600 minutes. They sing a song and they say how you measure life in a year, right? Okay. So what I'm going to do is I'm going to say, what if we compounded every minute? 1 plus 1 divided by 5,000, 25,600 minutes. And then some of you who know the song can't say that number without singing it. And then we're going to raise it to the 525,600. Can you do this in your calculator for me real quick? Do parentheses 1 plus 1 divided by 5,025. I can't say that. 525,600. And then close your parentheses. Make sure you hit the exponent button. For those of you on my calculator, that's that little caret button with a little raise to. Bless you. Bless you. Anybody get an answer? E? What do you mean E? It's the number for E. Keep typing it in and see if yours will come out to be approximately 2.718. Anybody getting close to that? Let me know if you're like way off of 2.718. You probably have a typo. You think you're way off?
Yes.
Make sure you do the caret button for the exponent. Yeah, raise 2.
Do I not do this?
No, you got it. And then do raise 2. And then the 5,500. Type that number again. Anybody else having trouble and way off? Oh, isn't that interesting? So if we compound every minute, we're really close to E. We could certainly change those minutes into seconds by multiplying that number by 60, and then we'd be able to say, like, what's happening if we do it every second. And you'll find by changing it to seconds, we don't see a whole lot of increase. But what we would do would get closer and closer to the irrational number that is E. So that's really how E came about and why E is what it is, as an FYI. Main thing you need to know from this is how to work the calculator. This is just for the curious people who want to know why is E 2.718. If you can just take my word as gospel and be happy with it, that's really all you need to know. Okay. Now, we are going to work on graphing, and this will be part of your homework assignment, graphing natural base functions. So natural base functions come in the form A times E to the Rx. And they'll be growth or decay depending on the value of R. And I'll talk about that in just a second, but I'll give you some time to write it down. Okay, so copy this into your notes. This will be important information. This natural base function is really just a special type of exponential growth or decay function. The fact that I say it is natural base means it has a base of E. So what that's really saying is, instead of working with our old equation, y equals a times b to the x, we're going to change the base b to e for all of our functions. So we would get y equals a times e to the x. But if I left it as y equals a times e to the x, I would only ever have exponential growth, because what's the value of e? We just talked about it. What's e? 2.718. Thank you, Eric. E is 2.718, which is always greater than 1. So then I would be saying that I could only have exponential growth functions with base e. But that's not true. Just the same way that like a population might grow exponentially, you might have something that decays exponentially with a natural base. And so we need to be able to have decay functions with e. Since e is always 2.718, the only way we can make it be less than 1 is to flip it, to have a 1 over 2.718 for our base. So that's why we add that extra r in the exponent. Okay, and that's why when r is greater than 0, we're going to have growth because our base will be 2.718. When r is less than 0, we're going to have a negative exponent, so e would technically be flipped, and 1 divided by 2.718, if you do that in your calculator, is a number less than 1. Okay. So here's how we can use this to graph a function. Go ahead and write this function down into your notes, put this example in. This is what I'll be expecting from you on your homework assignment tonight. It's very similar to what we did back on day 1 when we talked about exponential growth and decay in section 6.1. So we're going to graph the function for y equals negative 2.5 e to the x. What might be helpful to us to construct a graph for the exponential function? Jacob? What do you mean x? Oh yeah, it'd be nice to have some values for x. We'll plug it in, and then we'll get a value out for y. So what do you want to put in for x? Oh, Jackson, you're saying the numbers negative 1, 0, 1, and 2? So you want to use the same numbers we used back in section 6.1? Brilliant. Should that be allowed? I don't see why not. Let's do it. Okay, so let's make a table of values, or an XY table. Let's put the numbers negative 1, 0, 1, and 2. I'll give you some time to calculate those in your calculator, and then I'll call on you for your numbers here in just a second. So go ahead and calculate those in your calculator. Let me know if you're having issues with your calculator and you don't think you're plugging it in correctly. Here you got to type like negative 2.5 times e raised to the negative 1. And there'll be decimals, I'd say, round to the nearest tenth or hundredth. No, always the one that has the x. Does it have a mix on it? Always the one that has the exponent. So second. You can on this one, if you ever have substance getting multiplied, we need the parentheses. So if you want to get in the habit of adding the parentheses, it's not a bad idea. Yeah. Oh, okay. As long as the parentheses are there. If we do the second example, you'll be able to see what I mean. Yeah. Yes, ma'am? Yep. Yeah, Riley, Bailey, what'd you get for your number for negative 1?
Negative 0.9.
Negative 0.9. So if you got negative 0.9, you're on the right track. If you didn't get negative 0.9, you're not on the right track. Didn't you put in a positive 1? So what'd you get for positive 1, Kylie? So we did negative 1 first. 0 is my favorite because e to the 0 is 1, and 1 times negative 2.5 is negative 2.5. I could do that one without a calculator. Can anybody tell me what 2 is? In your table? Negative 18.4. Okay, good. Now raise your hand, call me over if you're not getting these numbers. We need to know ASAP if your calculator is not working properly. Plot those points. It's not a big deal that they're decimals. Just go almost to negative 1, but not quite all the way when you graph negative 0.9. So negative 1, negative 0.9. I'll use blue here. My calibration is a little off, so please excuse my marks if they're not exact. 1, negative 6.8, so I'm going to go almost to 7. And then, like a lot of people, for like negative 18.4, that's way off my graph. If you just want to mark a point way below your graph as like, okay, just so I know this is where my graph is headed, you can do that, or you can just leave it off completely if it's way too big or too small. Since we're doing exponential functions, that's very likely to happen on a lot of functions. So you can kind of ignore it if you want. But I'll just kind of mark to negative 18, I'm going to say is like way down there. Just like a little point, so I can keep track of it. Now, some of us may say like, gosh, those 3 or 4 points I plotted, I'm not really sure what my curve exactly looks like. I can kind of tell what's going to happen on the right side. Like to me, because I have that negative 18, this whole graph is going to have to just be like going down on the right side. Okay. And then some of us can piece back like what might happen on the other side. But I'll say this, if you're not sure what happens with your graph, pick more points. So like maybe I'm not sure what happens on the left side. I'm going to add an extra number to x in the table. I'm going to see like what happens at negative 5. I'm just curious. Where is my graph when x is negative 5? Can you guys type that into your calculator for me real quick? What is negative 2.5 e to the negative 5? Oh, negative 0.016. I'm going to say negative 0.02. That number is very small, right? It's almost 0. So when I'm at negative 5, I'm like super close to the x-axis. That must be my asymptote. Okay, so it has the same characteristic as the graphs in section 6.1. So now I know a little bit better like what's happening on that side and that this side is going down. So if you're ever concerned, like you're not certain that you have the right graph, you could always pick more points. Jackson gave us a good starting point, negative 1 to 2, but you're welcome to use more if you want. Can you do domain, range, and asymptote then? Should be able to. Okay, domain is all real numbers. It always is for all exponential functions, including natural base. Range in this case will be y's that are greater than or less than? Less than 0. And then just like before, our asymptote is always located at y equals 0. We don't have any vertical shifting yet, so we're kind of stuck at the x-axis until we have any kind of shifting. Now I have one final question I want you to talk about with the people around you. Is this graph exponential growth or exponential decay, and why? There are 2 justifications based on what we've talked about so far in the chapter that you could use. So talk with the people around you, see if you can convince each other. Is it growth or decay, and why? Go. Okay, let's hear it from someone. What'd you guys say, growth or decay, and why? Anybody? Jackson, I heard from you. I appreciate that you're always willing to answer my questions, so. Somebody new. Don't make Jackson do all the work. Jacob, you've also answered a ton of questions today, and I really appreciate that. Eric.
Okay, we need decay because negative 2.5 is less than
Negative 2.5 is less than 1. That was not your original answer, was it?
That's not R.
That's not R, is it? That's A. What was your guys' original answer?
That it was exponential growth.
Why did you say exponential growth originally?
Because as the graph function moves from the left to the right side of the graph, it is increasing its rate of change?
It's increasing in rate of change? Yeah, I would argue, and I've heard some groups around the room say it was growth because, because, how did you phrase it? It was going faster and faster as it went down. Okay, so that would be like what Eric is talking about with an increasing rate of change. Okay. In regards to what Eric was trying to say about growth and decay, something being greater than or less than 1, we have to look at the R value for that, right? So that would be the other way to determine if it's growth or decay. What is R in this function? What's being multiplied with x in the exponent? Do you see a number up there? No, so what is x, or what is R? It's really 1x. So it's x times 1, R is 1, R1 is greater than 0. So it is an exponential growth function. If you don't see a number with x, then it is 1. If you just see a negative x, then it is negative 1. So negative number in the exponent is really what you're looking for decay. We have one more thing we want to get down, and that is, what if instead of compounding our interest on a schedule at the bank, we compound our interest all the time? If we compound our interest all the time, we call that compounding continuously, and we have a new formula. So you have lots of formulas in chapter 6. This is already our, bless you, 4th or 5th formula in the chapter. When interest is compounded continuously, we're going to change from our compound interest formula, because if we say continuously, we don't have a number for n. When we say monthly, we know n is 12. When we say continuously, we mean all the time. There's no number for that. So we use E. And I call this your PERT formula. If you can remember PERT, then you remember the formula. P times E raised to the R times T. Okay. In this formula, P is your principal or your initial amount, just like it was for their compound interest formula. R is your rate, which needs to be a decimal, so don't put it in as a percent. You've got to change it first. And then T is time in years. You never plug anything in for E, you just use the E button on the calculator. Okay, so E is 2.718, and you can use the E function in the calculator. So here's an example. You deposit $10,000 into an account that earns 4.5% annual interest. Find the balance after 8 years if the interest is compounded continuously. Okay. As I'm reading that problem, when I get to the very end, if it says compounded continuously, this is a giveaway for PERT. If it says compounded any other kind of number, don't use PERT. Go through and find all the things you need, P, R, and T. What's my principal? How much my dad put in? $10,000, that's P. My interest rate is 4.5%. How will I change that before I plug it into the formula? Instead of 4.5, I'll use 0.045, right? Move the decimal place 2 to the left. Okay. And then how long am I leaving it in my account? 8 years. So that's my T. And then I'm ready to plug it in. So it's a little bit easier than the regular compound interest formula. I just do A equals 10,000 times E raised to the 0.045 times 8. Would you do this one also in your calculator? Like this is at issue, I want to make sure, Jackson, that your calculator does the parentheses for 0.05 times 8. Okay, so can you do this one, make sure our parentheses work? Eric, you're gonna have to do, like how you normally do your exponent first, you'll do 0.05 times 8, hit enter, and then do something else.
Yeah.
Anybody got a number yet? How many dollars are in my account? Hopefully more than 10,000. $14,333. And I'm getting a couple shakes of the head. Jackson, are you getting that?
I got 83,000.
Ooh. See, that's way too nice. $83,000? After just 8 years, I made $70,000. I'd take it. But that's way too good, right? So, do you guys have parentheses?
Mine didn't.
Okay, so retry it and see. Kylie, let me see yours. I've got a worksheet for you. I got it. Can't pass out. Nope, you gotta do time date in the parentheses. You can't close the parentheses on that. The parentheses have to stay open for both parts. Anybody else getting that 80,000 answer? Think about the reasonableness of your answer on something like that. Does it make sense for you to get $80,000? It'd be nice, just not realistic. Did everybody get a worksheet? Let me know if I did not pass enough back.